Hello and welcome to section 5.4, which is looking at indefinite integrals and the net change theorem. So in the last lesson, we looked at definite integrals, which had an upper and lower bound. And our most straightforward way of calculating your definite integral was to find the antiderivative big F to the function inside of the integral little f, and evaluate that at your upper bound and your lower bound and subtract these two answers. We ended up with an actual number because if we think about what this looks like on a graph, we have an actual function that we're looking at and we have a starting and ending point. So we have a finite amount of space underneath the curve little f of x. When we look at an indefinite integral, we don't have an actual number as our answer. We're going to have a function as our answer. And this is because the amount of space underneath the graph is not finite. So if I think about what this looks like graphically, if I have a definite integral versus an indefinite integral, let's say I have just a parabola. If we are actually evaluating this from some number a to some number b, this was the space underneath the curve, and we could actually find the amount of space that that occupies. If we have an indefinite integral, the problem is we do not have a starting and ending point. So this space is going to head off to the left forever and off to the right forever, and we cannot narrow this down to a single number answer. Therefore, the answer is represented as a function. The function here is still going to be the antiderivative, but instead of evaluating this somewhere, we're just going to still have an x inside if the variable we're using is x. And we must remember this plus c. Okay? This is our constant of integration. You must include this. The reason we did not have this in our definite integral is because technically we have f of b plus c minus f of a plus the same constant c. And so when you expand this, you get f of b plus c minus f of a minus c, and our c's cancel out. So we never needed c for our definite integrals because when we evaluate at an upper and lower bound, the c's from those two bounds cancel out with each other. When we are not evaluating, we must include this c at the end of our integration. So let's try one here. So if I want the indefinite integral of this function, we're just finding the antiderivative of this, but we must include plus c at the end. So the antiderivative of x cubed would be x to the power of 4. However, we normally would have something in front here because if I do the derivative of this, I get 4x cubed. So that doesn't work. I'm supposed to have 2x cubed. So if I'm supposed to have 2 instead of 4, I would need a 1/2 in front. The next one, the antiderivative of x is x squared. But again, if I do the derivative, I get 2x. I'm supposed to have 4x. So that means I need an extra 2 in front. And the antiderivative of 1 would just be x. And then I need my constant of integration, which is plus c, and I would be done. Okay. So do not forget the c. All right, let's look at this next topic here. So net change theorem. So hopefully we remember that f prime of x, our derivative, represents the rate of change of y with respect to x of our function f. So another way we could write this, f prime of x was also y prime. It was also dy dx. These were equivalent notations here. We used dy dx specifically when we did implicit differentiation, which literally meant change in y over change in x, or your rate of change of y with respect to x. Hopefully we also remember that when we were looking at position and velocities and acceleration, we had that velocity was the derivative of position, okay? And velocity is in meters per second. Position function was usually in meters. If our position was in feet per minute, then our velocity would be feet per minute. Okay. Acceleration would be the time squared. So if we used meters and meters per second, acceleration would be meters per second squared. If position was in feet per minute and velocity was in feet per minute, acceleration would be feet per minute squared. So if we wanted to integrate velocity, since velocity is with respect to time, we would use v of t dt. And when we do the antiderivative of this, the antiderivative of this should be your position function, which would be, if it's an indefinite integral, then you would have a plus c here. If you have a time 1 and a time 2, then this is going to be s of t2 minus s of t1. Now, if I think about this as the antiderivative of v being the position, and the derivative of the position is velocity, so essentially your antiderivative, your derivative. Okay. Velocity was in meters per second. Position was in meters. And if we think about dt, this is change in time, which would be units of seconds. Okay. So if we think about it, we're doing v of t times dt, or meters per second times seconds, which gives us an answer in meters. Okay. So if I integrate velocity, I'm going to get a position, and my integration of velocity, if that's in meters per second, your position function would be in meters. So in other words, if I integrate a function f of t dt, okay, the units of the answer are going to be the units of f times by the units of t. The same would be true if you had an f of x and a dx. This would be the units of f and the units of x. So our example was, if I integrate velocity with respect to time, and this is in meters per second and this is in seconds, then we're going to get a position function in meters. So that is our net change theorem right here. That would be your net change in position, or your displacement. So let's try a question. Consider a particle is moving in a straight line. The particle moves 5 units to the right and then 7 units to the left. Okay. Determine the distance traveled by the particle. Well, if I move 5 units to the right and then 7 units to the left, the total distance traveled would be 12 units. Okay. We get that by doing 5 plus 7. Now, normally when we're thinking about distance, we also consider direction. So normally moving right or forward was a positive motion, moving left or backwards was a negative motion. So this is the same thing as doing 5 plus the absolute value of -7, because moving to the left, we usually consider a negative distance. The displacement of the particle, displacement is compared to the original starting point, where did we end up? Did we end up in the same spot, to the right or to the left? Okay. So if I started at this point here and traveled to the right, and then started from this point here and traveled to the left, I end up over here, which is to the left of my original starting point. The question is by how many units? Well, this would also be 5 units, so this would be by another 2 units. So I would have ended up 2 units to the left of my starting point, which is -2. How I show that mathematically is I take my 5, which was my positive direction, and I add my -7, which is my negative direction, moving left, and I would get -2. So left 2 units with respect to the starting point. Now, if I think about what this looks like graphically, if I graph my velocity over time, so this curve here is our velocity, okay, the total distance traveled would be if you add up all the areas under the curve, because under area 1, that would be your distance traveled between time 1 and whatever this point is. The area 2 would be your distance traveled from this point to this point. And your distance number 3, or area 3, would be this point to time 2. So total distance traveled is all the areas added up together. What that looks like in terms of our integral is the integral from time 1 to time 2 of the absolute value of velocity, okay, which is what we did up here with our absolute value. Okay. So total distance traveled is the integral from the starting time to the ending time, depending on where you're looking at your distance for. And you would take the absolute value of your velocity. So what that means is we would add this one together, and then we would need to consider the positive version of this distance when we add that up. Displacement, you're looking at where are you with respect to your original point. So in this case, we would have A1 and A3 would be positive distances moving to the right of our original point, but A2 is a negative distance moving to the left of our original point, which is why we have positive A1 and A3 and negative A2. This is specific to this picture. And then our displacement would depend on how big these different numbers are. Okay, so our displacement would be negative if A2 is bigger than A1 and 3 combined. Our displacement is going to be positive, meaning we end up to the right of our starting point if A1 and A3 combined are bigger than A2. So when we want to find displacement, we take the same integral but without the absolute value. Okay. When we do the integral with an absolute value, we need to split that into cases. Okay, we need to consider what the different cases are, our positive versus our negative cases. Okay, so let's try a question that uses this. Okay, so I'm just going to write this at the top just so that we have it. So displacement is going to be the integral from t1 to t2 of our velocity with respect to time. Our distance is going to be from t1 to t2 of the absolute value of our velocity with respect to time. And when we do that, we need cases. Okay? Because when we think about absolute values, we pretty much always split these into a positive versus a negative case. All right, so it's asking us to find the displacement and the distance traveled over 0 to 5 for this velocity. Okay? So if I want to find displacement, we would have the integral from 0 to 5 of t squared minus 2t with respect to time. So that's going to be t cubed is our antiderivative of t squared, but I also need that 1 over 3 in front since there's no constant in front of our t squared. Okay. Minus t squared would be our antiderivative of negative 2t, and this is going to be evaluated from 0 to 5. So I do not need my constant of integration here because I'm evaluating it at actual endpoints. So this is going to give me 5 cubed over 3 minus 5 squared minus 0, which gives me 125 over 3 minus 25, or 125 minus 75 all over 3, or 50 over 3. And our units would be in meters for displacement. Our units should be the units of V times the units of dt. So this one is in meters per second, and this one is in seconds, so this one's going to be in meters. So we get 5 over 3 meters is our displacement. For our distance, if we think about what this thing looks like, okay, our velocity is t squared minus 2t. If I factor this, I get t times t minus 2. So I've got a 0 at 0 and at 2. And so this thing looks like something like this. Actually, let's make this just a little bit more clear. So when I want to find my 0, this is 2, and 5 would be way over here somewhere. When I want to find the distance traveled, I'm taking this area here and adding it up with this area here that's under the curve just till 5. So this would somehow intersect up here like this. Okay. So we have the negative case and the positive case, and we need to take the absolute value of this case plus this one here. Okay. So I need to split this into cases. Okay. So if I have the absolute value of t squared minus 2t, this is going to equal t squared minus 2t, the positive version of itself. Okay. If t is less than 0 or t is greater than 2, and it's going to equal the negative version of itself if t is between these two values. So when I find the distance, this is going to be from 0 to 5 of the absolute value of t squared minus 2t dt. When I split this into my two cases, what this means is my first case is going to go from 0 to 2, and it's going to be the negative version of our absolute value. Then our second case is going to go from 2 onwards. So in our case, 2 to 5, because the question told us we're only going up to 5, of t squared minus 2t dt. So we're evaluating two separate integrals here. So this is going to give me negative 1 over 3 t cubed plus t squared, evaluated from 0 to 2. We do the antiderivative. If it helps you, you can expand this negative in and rewrite this like this before you do the antiderivative. That's fine. Or you can do it all in one step. Just be careful with your negatives that you're not losing them. Okay. And then our next one, we would have 1 over 3 t cubed minus t squared from 2 to 5. So we get negative 2 cubed over 3 plus 2 squared minus 0 for the first integral, plus 5 cubed over 3 minus 5 squared minus 2 cubed over 3 minus 2 squared for the second integral. So this is going to give us negative 8 over 3 plus 4 plus 125 over 3 minus 25 minus 8 over 3 plus 4, or negative 16 over 3, so 125 minus 16 over 3 minus 25 plus 8. It's going to give us 109 over 3 minus 17. Make common denominators here. We're going to end up with 58 over 3. And again, this is in meters, and this is our distance traveled. And that is it for this section.